Here's an example. Imagine your network is a stack of simple operations, like linear transforms, ReLUs, whatever you want. Some have parameters, like the matrix transforms, some don't, like the ReLUs. When you apply your data to some input x, you have data flowing through the stack up to your predictions y. To compute the derivatives, you create another graph that looks like this. The data in that new graph flows backwards through the network, gets combined using the chain rule that we saw before, and produces gradients. That graph can be derived completely automatically from the individual operations in your network. So most deep learning frameworks will just do it for you. This is called backpropagation, and it's a very powerful concept. It makes computing derivatives of complex functions very efficient, as long as the function is made out of simple blocks with simple derivatives. Running the model up to the predictions is often called the forward prop, and the model that goes backwards is called the backprop. So to recap, to run stochastic gradient descent, for every single little batch of your data in your training set, you're going to run the forward prop and then the backprop, and that will give you gradients for each of your weights in your model. Then you're going to apply those gradients with a learning rate to your original weights and update them. And you're going to repeat that all over again many, many times. This is how your entire model gets optimized. I am not going to go through more of the math of what's going on in each of those blocks, because again, you don't typically have to worry about that, and it's essentially the chain rule. But keep in mind this diagram. In particular, each block of the backprop often takes about twice the memory that's needed for the forward prop, and twice the compute. That's important when you want to size your model and fit it in memory, for example.